offers no integrity protection, and the attacker, like let's say you're sending an encrypted file to somebody else. The attacker can flip bits knowing what file format you're opening, and if they have a, like let's say it's a JPEG image, if they have a vulnerability in that JPEG library that your OS uses to load it, they can probably pop other software on your system. There's a lot of other weird attacks you can do. You can use what's called a padding oracle to, if it's like an online service, continue sending mangled ciphertext over and over again, and based on whether or not you get an error, decrypt the original image. If you're going to do anything with crypto, you should adhere to crypto coding standards. These are common sense things that are well known among people who build and break crypto, but not really well known to developers outside of that niche part of the industry. The first one was actually a project by a well-known cryptographer. I don't want to butcher his last name, but he worked on Blake 2, SIP hash, and a bunch of other projects that you've probably heard of. If you're using random numbers, which most cryptography keys are random numbers, use the getrandom2assist call or dev-urandom. Never read from dev-random. Don't use random.org or any of these other crazy ideas either. You'd be surprised how much I see that in production. Oh yeah, I copied the demo code thing. As I said, we focus on PHP because of its wide market share. So the code examples that we have are in PHP, but the concepts are generally universal. So the first thing is to create a threat model. Client comes to you and says, hey, we need this done. Your first question should be, okay, how are people going to try to break it? Like, what are the security properties you're trying to assure? Do you want to make sure it's just confidential? You probably should worry about integrity too. If confidentiality isn't an issue, like it's a public ledger, like you're doing something with like certificate transparency, then you can just focus on integrity. What attacks can be attempted? Like, there's all kinds of examples that can go with that I can't think of off the top of my head. How should your application tolerate failure? So, as I mentioned, there was something called a padding oracle against CBC mode. There's other kinds of padding oracles, like against RSA. What this means is that if you are encrypting data and then you send it to your client and they flip a bit somewhere in the ciphertext, if it creates an error, that might give them useful information about what the decrypted data looks like before the error was produced. For example, CBC mode is typically used with a padding mode where if you have 3 leftover bytes in your block cipher, it'll append the number 3, like in binary 3 times. If one of those numbers is wrong, you'll get an error, padding error, failed to decrypt. That's actually useful for adaptive chosen ciphertext attacks. So thinking about how if, it might not be an active attacker, it could just be like a network error. Thinking about how the data could be manipulated and how that could affect the security of your what you're trying to build is very important, because in practice, a lot of the things that you think would be secure aren't because of attacks like that. And as I said, reuse Orthodox solutions where possible, even if you're doing something unorthodox. And anything that's not solvable by like, okay, if you need a stream cipher, use Salsa 20 or Cha-Cha 20. Don't use RC4. Don't invent your own unless you've been doing cryptography for like 20 years, and then get peer review. And also don't reason by Lego. When I said use authenticated encryption, it's very important that you use a mode that's given to you, or you build it very carefully. If you authenticate then encrypt, you create more side channels that people can exploit. CryptoFails covered this brilliantly. So the solutions we're using, there's 2 ways you can go. I'm going to show you the Libsodium way. These are for shared key encryption. This is no weird asymmetric stuff going on. These are the APIs you would need. Secret box, auth, PW hash. Straightforward. Public key, box, sign, key exchange. This is deceptively simple because Libsodium actually tries to make it as simple as possible to implement secure crypto. If you contrast this with using, since we're using PHP, using the OpenSSL extension and the native hash extension, your symmetric encryption becomes you encrypt with AES 256 in counter mode, and then you append a HMAC of your ciphertext at the end in encrypt in MAC mode. For authentication, HMAC SHA 256 is fine. Password hashing, bcrypt, cost factor 10. If you're using the password hash API, then you're already using that. If you need to derive a key, though, bcrypt actually wasn't designed for key derivation. It was only designed for passwords. So cryptographers typically recommend PBKDF2, which stands for Password-Based Key Derivation Function 2. Don't worry, it's in the manual. You don't have to memorize that. Okay, public key crypto with OpenSSL and the hash extension is where things get really messy. Currently, the best way to use it is to use what's called cont'd, where you encrypt the key and then you encrypt the data separately. So what you would do is you would generate a random 256-bit value. You would encrypt this with your RSA public key, and you get an RSA ciphertext. You would then use your random value and the hash, or the ciphertext in an HMAC to generate a derived key. You would use that for AES 256 counter and SHA-256 as with symmetric. And then you would send the RSA encrypted message and the symmetric encrypted a message, and if they have the private key, they can follow through the process and calculate the same key. This is the most, it sidesteps a lot of the constructions that lead to padding oracles, like if you use RSA and PKCS1 directly, there have been attacks published that are like 17 years old now. Actually, no, 19 years old now. It's been a while. Same thing with RSA for signing. If you're doing elliptic curve, then you're going to want to use deterministic ECDSA so you don't suffer the same failure that plagued the PlayStation 3. As you can see, this is kind of a mess. There's a lot of knobs and levers and things that can go wrong. What happens if you accidentally set E=1 for both these RSA things, like SaltStack did famously 4 years ago? Your security goes 0, because you're encrypting with RSA with E or D=1. You're basically just converting to itself. So for reasons that are obvious, the example code uses Libsodium. If you're doing anything in production and you don't have regulations like FIPS that tells you can't use Libsodium, you definitely should. So let's look at a weird problem. I thought I broke this one up, but oh well. You're running a website with a lot of privacy-focused people. This could be an activist group. This could be like a civil rights group. Like you could be doing like an outreach for like an LGBT youth group, and you don't want to store their IP addresses in clear text. But you still kind of need analytics for whatever business reason comes breathing down your neck of how much traffic is being used and by what variety of users. So, oh, okay, so that's what that did. So there's a lot of ways that I've seen people try to approach this problem. The first one is to encrypt it. But then you get into a key management question. What key do you use to encrypt the IP addresses? More importantly, it's reversible. If you have the key, you can decrypt it. So if you get a NSL saying we need all subscriber information, you give them an encrypted IP address, they could come back and say, hey, you have the key, you can decrypt it. So that's not a winning solution. Another straightforward idea people might come up with is to just hash it, like with MD5 or SHA-2. Unfortunately, for IP version 4, you only have about 4 billion possible values. Cryptographic hash functions are fast, and you can enumerate all possible inputs to outputs very trivially. So this is a solution that actually solves the problem. So you're going to store a random key. It can be stored in a file system. You can store it in memcached. It doesn't need to be super sensitive. It just needs to only be valid for 24 hours. You're going to use crypto-auth from Libsodium. It's basically HMAC. And then you will use that on the IP address and store that. And you'll get this random looking values that I wrote as hex instead of binary. When the day ends, notice that the same IP address completely changes the hash value because the key is different. For good hygiene, you're going to want to wipe the old keys after 24 hours. You could try zero filling the file, but if you're on a solid-state drive, that actually isn't reliable. Sam Baum had a talk at, I think it was 3 years ago at DEF CON about that. And now for the demo. So I don't actually know the IP address on the network or which subnetwork you would need to get to. I can actually find that out real quick. So if you go to 10.18.0.131, port 1337, you can actually see the demos on any of your devices. And if you do that, you'll create a traffic pattern that's more interesting than just the same IP address everywhere. Oh, there it is. Okay, so here's another weird problem that comes up a lot in different companies. Disclaimer that I was told by people in the cryptography community is that I should discourage you from ever doing this because it's bad and it's wrong, and you should, if somebody says, hey, we need this, you should definitely fight it. But if you lose that fight, this is kind of how you would want to approach it, okay? So you're storing passwords and you're securing them, you're hashing them properly. You're using bcrypt if you're on PHP, you're using Argon 2 if you're using Libsodium on any platform. If you're not using either of those, I hope you're using scrypt or pbkdf2. If not, then you definitely need to upgrade. And somebody says, well, you know, we know fraudsters are using duplicate passwords. We need a way to detect them or identify them for whatever weird reason. You know, they might have local regulations. No two users can have the same password for whatever business argument comes down from that you can't argue with. So here's some bad solutions. I always like to present bad solutions before a better solution, so you can kind of get an idea on why I went with the solution I did. Encrypt it with a secret key. This is similar to the IP address solution. Also, you're storing it in plain text if somebody has access to the key. Also, if you needed to detect it, like, oh, is this password already used? Now you need to go through, if you're using secure encryption, and decrypt every record in the database. If you have 1 million users, that means you need to do 1 million decryptions and verifications. Or you're forced to using like ECB mode or some other semantically insecure crypto, which is just bad, and don't ever do that. You can see the penguins is like the way a lot of people like to describe it. Some people might try to store an unsalted cryptographic hash, which totally undermines the security of bcrypt and pbkdf2 and all the other proper password hashing functions, which is what Yahoo apparently did with the MD5/bcrypt leak that came out earlier this year. So here's how I would approach the problem. These parameters might not be optimal, but what we're going to do is store a second password hash with a caveat. Instead of a per user salt, like what your API typically generates for you, we're going to use a constant. It's just used for differentiating uniqueness. Because it's the same password, it's the same salt, you're going to want to increase the cost a little bit, because if somebody gets a hold of your hash database, they might attempt to use that to optimize a brute force and go, oh, hey, 200 users have this password hash. If I attack this one, I got 200 accounts. In order to make the economics less in favor of attackers, you're going to want to raise the cost factors. Now, these are example numbers, and you might, in practice, want to raise them a lot higher. So in bcrypt, if you're storing with a cost of 10, you're going to want to go with at least 12. Argon 2, you're going to double the memory cost and increase the number of rounds by at least 1. These are lower bounds. You should probably try to go higher, depending on what your benchmarks allow for your hardware. And of course, there's a demo of this too. So let's create a user real quick. Let's just go with b-sides. This field, the SSN field, is for the next example, so I'm just going to fill in the pre-filled one. And what's a weak password? I know, password. Okay, let's add another user. Let's go with all the examples. This is going to the wrong page. I probably should have checked that. Here we go. So as you can see, they have a different hash. It's a little hard to see. Let me zoom it in. So this is an Argon 2 hash generated by Libsodium. You see the memory cost, the time cost, and the number of, or the parallelism degree. This is actually the same hash, but a different salt. If you look to the left, you can see that they are both the same password. But knowing this doesn't give you the password itself. There are threats where this does not fit with a threat model. Like, what if somebody obtains your password hash database a year ago, then they look at it now, or every month. Now that you have a password change history over time. And if you can actually crack some of those passwords, you can study the user's behavior and probably get into their other accounts. That's why when I first presented this idea on Twitter to my followers, well-known cryptographer said, yeah, you should really emphasize don't do that. So, kind of spoiled it a little bit. The third weird problem, this comes up a lot, especially in medical startups. They want to encrypt data in a database, but still be able to use it for like search operations, aggregation, or some kind of reporting. And usually this is from some ill-founded fear of SQL injection. Let me just say now, encryption is not a solution for bad security. So if you haven't encountered this before, you probably will eventually. There's three parts to this. You have the business goal or the government requirement. We need to store this information in order to do our job. Common sense in the industry is going to say you should encrypt it, obviously. You don't want social security numbers sitting around in your database as plain text, especially if you're like a lot of these medical startups and you have an open PHP MyAdmin from like 5 years ago. And you'll need to be able to search on them quickly, use them in select queries. Now this last requirement, being able to use them in a select query, like to find a user by their social security number, is similar to the password uniqueness issue, where it becomes a quickly, O of n operation, which should be O of 1. So first, can the database decrypt the values is the first question you should ask yourself. If yes, can somebody armed with SQL injection? Chances are, if you said yes, the answer to the second question is also going to be yes. Are we using secure encryption that's indistinguishable from random noise, has integrity protection, and is like one of these modes? AES GCM is what you probably use to connect to Google unless you're on a smartphone. XAlso20 Poly 1305 is what Libsodium uses for its encryption. And can we avoid reading and decrypting every record? Because we don't want to do that O of n problem. We want O of 1 for that. So there have been a lot of research projects trying to solve this problem. One of them is called homomorphic encryption. This is to where you encrypt data you store in your database, and the server can do a calculation, like multiply it times 4, and give you back the result. And when you decrypt it, it becomes a valid plain text. They typically use lattice-based systems or unpadded RSA to achieve this. It doesn't provide integrity protection. It isn't indistinguishable from line noise. The ciphertext has structure, and that structure can be exploited. Another one that popped up late last year was order revealing solution, order revealing encryption. But like ECB mode with symmetric, you can see the penguins. It's not semantically secure, and yeah. So these solutions can basically be summed up as, if you want side channels, implement them. They're experimental work. There's a lot of great minds working on this, but they're too interesting to be used in real-world software. We want our crypto to be nice and boring. So let's revisit our ground rules. The first one was always use authenticated encryption. Let's start with that. So my solution that I'm going to propose uses 2 columns and 2 keys. One of them is just your ciphertext as normal, using an authenticated encryption cipher. And the other one, these are your modes you could choose from, is what I call a blind index. A little bit more detail on how they're implemented. Typically, you would just take a second key and do like a HMAC of your input with that static key, and that would be good. But if you're doing a low input, like most of the time you're going to be, you're going to want to use something like Argon 2, because if somebody manages to get all of the blind index values, if it's a fast hash like SHA-2, or even if it's HMAC SHA-2, they're going to just burn through all the possible values quickly. So if you take the input you're trying to search for, like let's say a social security number or like the last 4 of a credit card number, and you run it through this operation, you can use it in a select query safely without leaking any useful information about what's encrypted, other than does it match or no. And that's similar to what's going on here. If I return, so let's go 1, 2, 3, 4, 5, 6, 7, 9, 0. And that was the value I entered for Jane Smith earlier. And you can see these are all different values, including somebody else who created one to test if the code actually works. So we're using crypto secret box from Libsodium to encrypt the data. The demo code uses actually crypto PW hash for password hashing, which is Argon 2, just because the demo itself uses social security numbers. I thought that would make more sense. But your general construction looks like that. You pull it from the database and you decrypt it. I don't think I actually demoed the decryption, but I unit tested that. We avoid all these crazy homomorphic schemes, and you use known primitives. You use the Orthodox solutions that cryptographers have been banging on for years and not found any weaknesses in that are practical anyway. There are limitations here. You can only use it for an exact lookup. If you're looking for like the first 8 of a social security number, that's not going to help you any. So what if you need to separate case-insensitive and case-sensitive searches, for example, for like person's name, if you're encrypting everything? What if you need to be able to search on a subset of the data? Like, does the first 3 letters of your name match? The general solution would be to make a separate index for each use case, which might sound very expensive, but there's something else you can do. If you're more concerned about storage than you are about CPU usage, you can just truncate the hashes that you get from these operations and use them as a Bloom filter. So you might type in like the first 3 letters of John, and you might get 5 different results with different ciphertexts. And then you go through a much smaller subset, and you still have an O of N solution, but you have less storage. So to recap the solutions, if you're logging IP addresses anonymously, HMAC with a daily random authentication key, duplicate password detection, Argon 2, or HMAC with a random salt, or static salt, excuse me. Encrypted database search, authenticated encryption with a blind index. No crazy homebrew primitives, no experimental academic designs. Does anybody have any questions? Okay, well, everything's open source. You can look through the code, you can look at the slides. My contact information is on the very first slide. So if anybody has anything you want to ask me about, I'll be around here for most of the day, and you guys can reach me online. Thank you.